Good morning. Welcome to Chapter 8 of JavaScripts. This is algorithm and programming language. Covers several things within this chapter. So let's get right into it. You've been using algorithms all your life. Now you're thinking about them more as you become a programmer, a computer scientist. Whether you're going to be doing databases or whether you're going to be doing JavaScripts or C++, it doesn't matter. You will be thinking in terms of algorithms. So we can say that algorithms are underlining of all computer science computation. Remember, they are a step-by-step sequence of instructions, and you do this every day. If you have children, you do it a lot more because you have to a lot of times give them a step-by-step instructions of what you want them to do. And it's amazing though that as you do that, it becomes apparent that you're able to leave out a lot of steps when you're talking to another human. We'll discuss this in a little bit. In that, what you should do is think about giving yourself an algorithm. Create an algorithm where you're able to changing colors on y'all. You're able to accomplish an objective. Now sit down and think about it, and guess what? You will have left out lots and lots of steps that you would have to give a robot or a machine or even a child to do something. Because there's certain things when I say write an algorithm for getting out of a room, you'll say I stand up, walk to the door. You left out hundreds of steps that has to be programmed into a robot. And many times with a child, you might have to tell them, first turn the chair a certain way, then stand up, walk to the end of the aisle, then turn right and walk down the end of that aisle, turn right to walk out the door. So you have to start learning to think in steps and realize that the machine cannot take a gross instruction and know what to do. It has to be detailed for the machine. So as we continue to slide 3 here, think about a recipe for baking cookies. This always brings back a hilarious incident in college in trying to make cookies. And the people I was assisting with on making cookies, they left out one instruction because they was doing it from memory and not having it written down in front of them. And that taught me a very valuable lesson to write stuff down. So in the excitement, you would not forget. They also go into details about how a recipe written for a master chef would look different than for a college student. And the reason for that could be is there's certain skill set that the master chef has already learned and already knows. And so you don't have to tell them to preheat the oven or to preheat it even at a certain temperature maybe. They just know this from experience, whereas a young college student would not. You have to remember that with your computer, it's not a master chef. It's not even a college student. It's a dumb machine. You are the one giving it the brains. So that's why they talk about that in this little paragraph about how demanding computers can be. Now, here's a nice 4-step plan on solving problems that I would suggest you write these down somewhere. And whether if you're a math major, you can see how this is useful in math. Even if you're a biology major and you're looking at information science or informix as your major or minor, you've got to do these things. You got to understand the problem. Then you got to devise a plan. Then you got to carry out your plan, and then you got to examine the solution. You go, oh, the plan worked, but was the plan detailed enough that you could hand it off to somebody else and they were able to repeat it? And that's exactly what we're having to do in computer science, is make sure things are detailed enough that we can follow through with it, or the machine can. So in looking for the oldest person in a room full of people, you can simply say, hey, yeah, I've got a room full of people. We want to identify the oldest person in the room, and you're going to make assumptions. And that's true for everything we do in life. There are certain things we have to assume that the person will give their real birthday. If two people are born on the same day, they are the same age. We know that's not true in a college class. They can be on the same day, but different years. And I think you only need something like 50 people, I think it is, for you to be able to have two people with the same birthday, not year. So walking through this, we will look at two different ways to solve this problem. So the first one they called algorithm 1, and you line up all the people along a wall. You ask the first person to state his name and his birthday, and you write that down on a piece of paper. You then go to the second person and ask them, or tell them their name and their birthday. If the second person's birthday is older than the first person, you scratch out the first person and write down the second person. You continue doing this until you get to the end of the line. And when you get to the end of the line, the person's name and birthday that is you last wrote down is the oldest person. Simple, straightforward method of doing solving that problem. Now in algorithm 2, again, you line everybody up against the wall, but then you have everybody pick a partner, and you can see here that they pick two people right here, two people here, and so on. These two people are asked to tell each other their birthday, and the person with the oldest birthday will then step forward, forming a new line. So all of a sudden, you cut this 2, 4, 6, 8 people in round 1 down to 4 people in round 2. Round 3, you cut it down to 2 people, and then by round 4, you have the oldest person in the room right here. This is very fast way of doing it, and that's key. If you want to make sure this algorithm works, you'll pick the first one. Very time consuming, but you're walking down the line. In algorithm 1 involves asking each person's birthday, then comparing it to the birthday written on the paper. Amount of time to find the oldest person is proportional to the number of people. If you double the amount of people to find the oldest will also double. So the time will double as the number of people double. So it's proportional. Now the time needed to find the oldest person is proportional to the number of rounds it takes to shrink the line down to one person. This is for algorithm 2. It turns out that this is a logarithm on base 2 of the number of people. If you double the amount of people in using the algorithm 2 method, the time needed to find the people increased by the cost of one more comparison. Very efficient. Now, remember the difference between an algorithm and a logarithm. Algorithms are a step-by-step sequence of instructions. Log is the exponents to which a base is risen to a new product number. Now it's very interesting when you get here, and we're going to compare. Let's say it takes 5 seconds. Assume 5 seconds to compare birthdays. Again, we make an assumption, but if you had 400 people using algorithm 1, it will take 2,000 seconds. That is 33 minutes, over 33 minutes to do that. It's about 16 minutes to do it with 200 people. Now using algorithm number 2 though, and again we're going to do 400 people, because we're doing the comparing and eliminating, it takes only 45 seconds. This up here is in minutes. This is in seconds. Big difference in the amount of time. This becomes important when you're doing large databases, maybe even large as in doing a few thousand records, but nowadays we're looking at millions of records at a time. So here we're looking at what is called the big O notation, and the big O to N require time proportional to the size of the problem. The big O log of N requires proportional to the algorithm size problem. So 2 is a log N big O problem. So in searching a common problem in involving storage and maintaining large data records, and more we're dealing with huge data records nowadays, and it's not going to go away. So it's going to become bigger. So there's 2 common approaches that we use as we begin to refine the algorithms. Is the sequence search, which is a nice general purpose but very slow, versus a binary search, which has restricted use but is fast. So let's look at those. In the sequence search, you start at the beginning and you go to the end, or you go until you find the record. This is like an old cassette tape. Whether it's 8-track or after 8-track, we had the cassettes in cars. To get to song number 14, you had to quickly go through songs 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now you hit 14. You would always overshoot and had to back up in most cases. Then they came along with things that would help find it, but you still had to spool the tape through that. It took forever to get to your favorite songs. Then along comes CDs, which could jump to a record, which is a good binary type. But anyway, this is not practical for large databases, complex databases. Of course, the worst case scenario is what you're looking for is the very last record. If you got 1,000,000 records, it could take you days to get to it. Remember the old science fiction movies that had the big reel-to-reel tapes on the wall turning? Those are data tapes, and to get something, you had to spool through it. So the binary one, though, is basically you have to have a list in order. And so their example here is a list of numbers that are in increasing orders, or a list of numbers and words in alphabetical order, and you would start in the middle. And so there was your beginning range. So please read these, because these will become important as you try to find information. And so what you do is you examine them, and this potentially cuts your range in half every time you do a binary search. It keeps cutting them in half until you finally find them. So here you start examining at the middle entry in the proportional range. If the middle entry is the item you're looking for, then you're done. If the middle entry is greater than the desire, then reduce the range that's to the left of the middle and find the middle of that new and start all over. And eventually you'll go, it's less, it's less, it's less, up, it's up, higher, boom, I got it. Here's an example of them doing that. They start with a middle entry. What they're looking for is MD, so they start with ND, which happens to be at the middle of the records. And so ND, they immediately eliminate everything from here back. We don't have to look there anymore. So next it will examine for the middle of the new cases, which are here to here. And what it will do is find the middle of that. And of course, this one actually start back up here. We find the middle here. We know that this is too low. So you see here that they eliminated everything from IA back. We now have our new set, which is here. And we start with the middle, and lo and behold, MD is the middle. If it wasn't, then we would either go left or right again, eliminating everything until we do have it, which would end up in the middle, which we find it. So sequence searches work very nicely if you have lots of time. It is considered a big O of N search. You start at the beginning, you go to the end. In doing binary searches, these are log of N of the big O, and you start splitting things in the middle. There are many types of search algorithms out there, literally dozens and probably hundreds, depending on how complex you need to get. You'll learn more about these later on, especially in your other classes, especially in database classes. So here they give you an example of doing it two ways. So read that. Newton had a way of finding the square root of a number that was very efficient, and y'all can read that yourself. So programming is all about designing and coding algorithms for solving problems. Precision is very, very necessary to write programs. It can be very frustrating, as some of y'all have already told me in emails, and it is frustrating as you're learning a new language. Now, if this helps, it's easier than it was 50 years ago. And even in the late 70s, when I was learning Fortran and using punch cards and all that, it was easier than what the original folks had to do when they were working with something like the ENIAC, which had to be wired, literally wired to make it work. Not just turn switches to either on or off, but actually the wire had to be put in. Very, very time consuming. With the von Neumann architecture, what we talked about yesterday, coding instructions became easier to handle. We still went from machine language, from machine language, which here is an example of machine language, folks. Like I was telling you yesterday, it's all in zeros and ones. And it's 8 of these combos that would make up a word. Now, from machine language, we would move into assembler where 8 of these ones and zeros will become like the word add. So things have progressed nicely. I had a course in grad school where the professor could write stuff on the boards in ones and zeros. I bought a calculator that I could punch in his stuff and get what it was. So let's continue. We move into the world of the high-level language. And we keep advancing this. And what we want to do is get to a ability to talk to the computer like you see in Star Trek. I know some of you may be laughing, science fiction. But in Star Trek, a lot of times they simply talk to the computer and it figures out what it wants for what you wanted. That's a lot like my Alexa that's sitting on my desk here. No, it didn't go off when I said the word Alexa because my wife went in and changed its name. So we can tell it certain things we want, and it immediately goes and gets that information like weather. An example, computer, weather.
Right now in Madison, it's 53 degrees with rain. Today's forecast has showers, with a high of 53 degrees and a low of 26 degrees.
So this is what we want to get to eventually with all computers, is to simply be able to talk to it and talk to it with our own cultural and personal idiosyncrasies, and it will go out and find the information we want. We're not there. So in this slide, they're showing you an example of here is a JavaScript asking you to do something, and here it is in the same request, but it's in C++. And so you can see how there is a difference there in the way the two languages work. One of the beauties of C or C++ is it is very compact for what it does. Something else I wanted to point out while this slide is here, that this is the main function. Remember, we talked about functions in Chapter 7. And over here, we're not showing any functions. I wish they wrote this example here as a function to show you. But in C, C++, everything you do is a function. You have the main function, which calls all the other functions. So all programs that you write, even at the high level languages, have to be translated into machine language first. There's two standard ways of doing this: the interpreter or interpretation, or the compiler or computation, compilation. So C++ uses a compiler. JavaScript is interpretive, so is Python, several other languages. So an interpreter provides a real-time translation. The advantage is it's immediate. The disadvantage is if something fails, gets an error, corrupted for whatever reason, you must resend it. It must be reinterpreted. With a compiler, once you translate it, it can be read over and over again. So that's real advantages of that. You don't have to wait for the interpretation to happen. It's already done. Here's an example they use of doing an interpreter versus a translator. And so there is cause in the world for both of these to exist. And their example here of doing a translation from the Chinese to English real time. If you ever watch stuff from like United Nations, you'll see people with headphones up to the ears, and what they're doing is they're hearing an automatic translation of what the speaker is saying at the podium. And if you'll sometimes they'll show you in a glass booth up around where the people are on the floor watching, there are translators. And let's say you have 12 different people at a table listening to a 13th person speaking. He's speaking Chinese, and these other 12 people each speak a different language, whether it's English, French, German, Hindi. You have to have a translator back there who is hearing the speaker and immediately saying what he is saying in the language that the person around the table can hear. There's a lot of work being done now for automatic translator, machine translator, and there's a couple of companies advertising those. Those are coming out. That will be fascinating when they come, because they're available that you can like hear a taxi driver, he can say something, it immediately translates it into English for you. You say the English and then play it back for him almost immediately within seconds of what you're saying, but then it says it in their language. It'd be great for like with taxi drivers whose English may not be the best. Most of my travels in Europe, their English was actually better than ours. So here's an example of JavaScript doing an interpreter, and here's the code. It goes from the code to the interpreter to what you see on the screen. And this walks you through it. Just understand how all that is happening. in a compiler, then this is what happens, and its output is machine language, and then you have to execute the program. It produces an exe file. You execute the program then, and then once you execute it, it goes to the screen. So there's always trade-offs. They're discussing the trade-offs here between interpreter and compiler. Uh, Understand these. Could be a good test question to ask y'all, but you need to know when people start saying, well, why are you doing interpreter? Nobody uses interpreters nowadays. Well, yeah, they do. And here is the reasons why. And here's the advantages of compilers. Well, anyway, that ends chapter 8. Have a good day.